I'd like to now talk about the alpha addition of ketones, and as I said earlier, the alpha position is defined as being the carbon or the hydrogen next to the C double bond O. So this is the alpha, that's the beta, etc., etc. So we're talking about addition of an alkyl group to either this carbon or to this carbon in a symmetric system. In the first step, what happens is we use LDA, which is called lithium diisopropyl amide, which is a very strong base. So this is a very unstable type anion. You can see that the conjugate acid is pretty stable. It's going to be diisopropyl amine, and this is lithium diisopropyl amide, a very unstable anion. So it will remove the somewhat acidic alpha hydrogen here. The reason this hydrogen is even somewhat acidic is because the anion can be stabilized by resonance with the C double bond O that's right next to it. I want you to note that it's not possible to take off the hydrogens from here or here or here because these would not be stabilized anions. So it's always the hydrogen on the carbon next to the C double bond O that will be removed. And then we can have the negative charge come in and attack the alkyl bromide in a displacement process like an SN2 to produce our alpha substituted ketone. Alright, let me show you that mechanism with an example. And here's an example here. We do this at low temperature because the LDA operates best at that. We're looking at kinetic conditions. Stops other unwanted things from occurring. We want this proton removed. We don't want anything else to happen. You'll notice that this is a very hindered base. That is, there's a lot of stuff going on around the negative charge. That prevents the negative charge coming in and attacking the C double bond O, for example. That's because there's just too much stuff around the N negative. But what it can do is attack an exposed proton like this alpha hydrogen right here. So that's what we'll do. We'll attack that. We'll get a negative charge on the C. And a negative charge then will come in and attack the alkyl halide like this. And then we will end up getting our product. Alright, so that's one way of doing it, but that requires some pretty heavy conditions here. We use LDA, a very nasty base, minus 78 degrees. The conditions have got to be completely dry. You can't have any water around this because it will just take the proton straight off water and won't even react with your compound. So there are other ways that we can put an alkyl group into the alpha position as well, and that's by the enamine assisted nucleophilic addition, where we use piperidine as a catalyst, piperidine and acid as a catalyst, and you can see we get these enamine salts that can end up being converted into these alkyl type alpha position, alkyl substituted ketones, where the alkyl group ends up in the alpha position. And these are usually higher yielding and a little bit more convenient than these reactions with the LDA at minus 78 degrees.